This brings us to the second part of this video. So far in the first part, we've been talking about features in 1.1 that can be thought about as features that are evolving from 1.0. In the second part, we're going to be talking about features that are basically just new stuff. First on this list is a facility called Coroutines. So Castor now allows you to define coroutines in C++. These turn out to be a very useful facility for defining relations imperatively. Then we also have a new relational operator called the take-left operator and a class of relations called take-left relations or TLRs that go along with the operator. We also have a bunch of relations called aggregation relations. Let's now talk about coroutines first. As I said, coroutines turn out to be a very useful facility for defining relations imperatively in C++. And for this purpose, for defining coroutines, we have a few primitives that are provided by Castor. The first is a class called coroutine, and then we have 4 macros: cobegin, coend, coyield, and coreturn. Let's just quickly take an overview of what coroutines are and how to define them in C++. Before talking about how to implement coroutines in C++, I'm going to cover the concept of the coroutine itself briefly here. I'm using some pseudocode here to define a coroutine. This is pseudocode because C++ does not natively support coroutines. So here I'm trying to define a coroutine called range, whose behavior is similar to the range relation that we have in Castor. Here I've specified the return type to be bool so that it can indicate whether it's done generating all its solutions or not. If it returns true, then it has generated a solution, and if it's false, then it's out of solutions. It has 3 parameters. The first one is a logic reference I, whose value is in the range, in the inclusive range denoted by the next 2 parameters, first and last. If a value is defined for I, then we merely check if the value is in the range and return true or false accordingly. If I is not initialized with the value, then we proceed to this loop where we will be generating values for I. So starting from first, we keep incrementing the value of I, and each time we return back to the caller. Now we return back to the caller using a yield statement here. What it does is merely remember the point at which the transfer was returned back to the caller, so that the next time around when the caller invokes this coroutine, the control does not enter the coroutine at the very beginning, but instead it resumes from this line and goes back into the loop and continues incrementing the value of I, and again returning true if I is less than last. And once it's done generating all the solutions, it simply resets the value of I back to its uninitialized state and returns false, indicating completion. Now here we are triggering the coroutine. Each time we invoke range, it returns true. We go into the body of the while loop, print the value of I, the current value of I, go back into the while loop and get the next value of I by invoking range again, and print the value of I, and this cycle continues till range returns false. Notice how the control is basically transferring between this while loop and this for loop here. So both the caller, which is the main function, and the callee, which is the range coroutine, both resume execution from the point where they left off last. So this creates sort of a sibling relationship between the caller and the callee. This is different from subroutines, where they always start execution at the very first statement. So in that sense, subroutines share a child relationship with their caller. Just to make the resume semantics of coroutines a little bit clearer, let me replace this for loop with the equivalent while loop. The semantics are the same, but here we have a little bit more clarity on which statements are executed where. For instance, the increment happens at the end of the while loop, the check at the beginning, and the initialization prior to that. And the yield is in the middle of the loop. Now, when the while loop here invokes the coroutine for the first time, the execution enters at the very first statement, then proceeds all the way up to this while loop here. At this point, we have I initialized to first. The check succeeds, and we return back to the caller. Now, at this point, I is initialized to whatever first is. In this case, first's value is 1. So we print 1, go back into the while loop, invoke range again. At this point, we start execution of this coroutine at this point because this is where we left off last, and increment the value of I, go back into the while loop, and then return back to the caller if the check succeeds. Now at this point, a natural question is perhaps, how do we start a completely fresh execution context of a coroutine? So for instance, assuming we have just iterated over this range here, and now we are interested in iterating over this range, 4 through 8. These two iterations are completely independent of each other. So we don't want range over here to be resuming from where it left off over here. We'll take a look at how this is addressed as we start implementing these coroutines in C++ using the primitives that are provided in 1.1. Let me switch to slides to explain how to define coroutines in C++. To the left here is the same pseudocode for the coroutine range. And to the right is the skeleton C++ definition. As you can see, the basic idea here is to turn the coroutine into a function object. The base type we use here is a class called coroutine, which is provided by Castor. The function call operator must have a return type bool, and the statements in the function call operator are bounded by these two statements. These are macros, co-begin and co-end. The parameters to the coroutine are turned into parameters to the constructor and stored away as data members. This allows these values to persist across function calls. Next, and the final step, is to simply translate this coroutine's body directly into C++ simply by replacing the return statement with co-return macro and the yield statement with co-yield. And that's basically all there is to defining coroutines in C++. The one thing to keep in mind is to avoid defining any local variables within the body of the function call operator, as the values for that local definition will not persist across function calls. Such locals should be promoted to data members so that the values can actually persist. If you do require any local variables that do not need to persist across function calls, you could just define them just prior to the co-begin statement. Now let's look at how to actually use these coroutines. To the left again is the same pseudocode we saw earlier. First we're iterating over the range 1 through 10 using I, and then over the range 4 through 8 using J. Here, the first execution context is started off simply by instantiating the range function object and then iterating over that using the function call operator. And similarly, we instantiate yet another execution context by simply instantiating a second function object and then using the same while loop. The body of the while loop, as you can see, remains unchanged. Take a brief look at the macros we've used to define coroutines. We have basically 4 macros: co-begin, co-end, co-yield, and co-return. These macros rely on an integral data member, which is introduced by the class coroutine, which is the base type. It uses this integral data member to remember the point at which execution should resume on next invocation of the coroutine. The yield and return macros should only appear within a begin and end block. The co-end macro has an implicit built-in return false statement, which basically implies that any statements following the co-end macro will not be reachable. What this means is this macro should preferably be the last statement in the function call operator's body. Similarly, the co-begin macro should be the very first statement in the function call operator's body. If you choose to actually insert any statements prior to the co-begin statement, be aware that these statements will be evaluated on every single invocation of the coroutine prior to resuming from wherever it needs to resume. The co-yield and co-return macros are used for suspending the execution of the current invocation of the coroutine and returning control back to the caller. As part of returning back to the caller, you provide a return value, which is a Boolean value, true or false. If the return value is true, you've indicated that the evaluation succeeded for the current invocation. And if the return value is false, it indicates a failure in evaluation of the current invocation. When you suspend execution of the coroutine and return to the caller, you have one of two choices to make in regards to what behavior should be exhibited when the caller invokes the coroutine once again. You can either decide that the coroutine should resume from the point at which you are suspending it, or you can decide that the coroutine should terminate its execution context and all future invocations should merely return false immediately. Co-yield with argument true is the only way to support the resume semantics, and all other combinations of co-return and co-yield will terminate the execution context. Terminating the execution context is nothing but setting the resume point at the co-end statement. If you recall what I said earlier, the co-end statement has a built-in return false. So basically, when you're terminating the execution context, you're skipping the entire body of the coroutine and directly jumping to the co-end statement, which will return false to the caller. For more information on these macros, along with some illustrative examples, please refer to the reference manual on the section on coroutines. Now let's answer the question as to what coroutines have to do with relations. Coroutines are actually the facility to implement relations imperatively in C++. The coroutine range that we just defined is also a relation. So there's no real difference between relations and coroutines as such. There's one thing, however, which is in terms of requirements. Relations are expected to be able to participate in backtracking. Therefore, they need to revert any externally visible state once they're done. So let's take a look at the earlier slide. Notice here there are two parts to this coroutine. First is if the value of I is originally defined, and the second part over here is when it's not the case. If I is already defined, then we do not modify the value of I, whereas if I is not initialized, then we generate values for I. So in that sense, we are modifying I from its originally undefined state to some defined state. So therefore, at the very end, we revert back the value of I to its originally undefined state. This requirement to undo any side effects is not essential for coroutines, but essential for relations. So this is the only real difference between coroutines and relations in C++. It is often desirable to define generic relations or coroutines In such instances, we use a standard C++ pattern of providing an additional inline wrapper function which merely instantiates the generic function object. This pattern helps with automatic template parameter type deduction. So as a user, you don't need to explicitly specify all the parameter types and use a simpler syntax as in the case of the second bullet here. Often when defining generic relations imperatively, it may be desirable to be agnostic about whether a particular object you're working with is a logic reference or not. In such cases, it's useful to use this helper function called effective value, which will dereference the object if it is a logic reference, or else it simply returns the original object. Similarly, there's also a traits class called effective type. It defines a member type def called result type, which will be same as T in the case of ordinary types, whereas if the type T is a logic reference, it's specialized so that result type is actually the value of the type referenced by the logic reference. Coming to the next major feature in 1.1, we have the take left operator. The take left operator is also a binary relation, just like the AND and OR and exclusive OR operators from 1.0. It takes two arguments. The first one is an ordinary relation, and the second one is a special kind of relation called as TLR. We'll take a look at TLRs in just a moment. The reason for introducing this operator is to simplify the syntactic overhead required to handle a specific class of relations which have this one particular requirement that they need visibility on the entire input range before computing a value. Most of the relations that we've seen in 1.0 were able to simply look at one input value and produce a corresponding output. However, there's a category of relations which require visibility on the entire input data set before actually being able to produce any result. Here are some examples of such relations. You can think of aggregation relations like computing the max or min of our input range. These relations will require to examine all the values in the input before they can actually declare which item is the largest or the smallest. Similarly, we have ordering algorithms which could order the input range based on a certain criteria or simply reverse the order of the elements in the input sequence. Now also, grouping is yet another such example where you may want to group a set of elements based on a certain property. And you could conceive of other such relations which have this requirement where they need full visibility on the input data set. Semantically, this operator is very simple. All it does is repeatedly trigger the evaluation of the TLR, which is RHS here, and passes the ordinary relation, which is LHS, as argument to the TLR at the time of evaluation. So this is the only difference between a TLR and ordinary relation, that ordinary relations do not take any arguments at the time of evaluation, whereas TLRs take one relation as argument at the time of evaluation. So let's take a look at some example of using this operator. Let's take a look at the simple example to understand the usage and workings of the take left operator along with TLRs. In this example, I'm using the TLR max. This expression here will give you the largest even number in the vector v. Here v is a logic reference to a vector. This expression to the left of the take left operator is itself a relation which is generating all even numbers in the vector. And then we proceed to feed it to the TLR max. which will give you the largest I. So in this sense, actually I is working both as an input and output argument, because I is used to observe all the even numbers that are generated by the relation to the left of max, and also max uses I to generate its output. Now once we put the whole thing into motion by triggering the evaluation on R, we have the largest value in I printed to the console. Now it is possible to rewrite this entire expression without using the take left operator, and that will give us some insight into how the take left relations operate. Here we have R, which is actually the same relation which is to the left of the take left operator. So R generates all the even numbers in the vector, and M is just max of I, which is the right hand side of the take left operator. In order to trigger the evaluation on M, which is a TLR, we need to provide it a relation. As I mentioned earlier, TLRs require a single relation as argument at the time of evaluation, unlike ordinary relations which do not take any arguments at the time of evaluation. So here we provided R as an argument to M. So now max actually has access to both R and I. So it uses R internally to repeatedly trigger the evaluation on R so that it can observe the values generated by R in I. This allows max to have visibility on the complete set of results generated by R, and then once R has been exhausted, then it proceeds to use I to generate the largest value. In summary, the take left operator is just a syntactic shortcut for the more verbose syntax that you see below. Its primary job is to provide a mechanism using which TLRs like max can get access to the entire input sequence prior to them being able to generate a solution. Here's a listing of the TLRs provided in 1.1. We have average for computing averages, max and min for computing the largest to smallest value in a sequence, sum to compute the totals, reduce, which is similar to the standard algorithm accumulate. Then we have 3 TLRs for sorting. We have order, which will just order objects based on the default less than operator or based on a custom comparator. We have then order underscore mem and order underscore mf, which are provided primarily for syntactic simplicity when you are ordering objects based on the value of a data member or the value returned by a member function. Then we have reverse for reversing the order in which the elements were generated, count for counting the number of times the other relation succeeded, which means the number of solutions is generated. We have group by for grouping objects based on any criteria. Group by also supports nested groupings, and nesting levels can be arbitrarily deep. One thing to keep in mind in all of these TLRs is that they do not provide test mode support directly. However, we can simulate that behavior using one of the unification functions like EQ. So let's say, for instance, you are interested in checking if 55 is the sum of the first n numbers. You would first go ahead and generate the sum as follows, and then use the unification function to check if the sum is equal to 55. There's also a few relations being introduced called aggregate relations. These relations are simple ordinary relations, so they will not be used in conjunction with the take left operator, unlike the TLRs. We have average, max, min, and so forth, which you can see have similar names as some of the TLRs that we saw on the earlier slide, with the only difference that we have an underscore off suffix to distinguish them. These relations work directly on the containers on which the aggregation is to be performed. So if you already have a vector on which you want to perform the aggregation, then you would probably prefer to use these instead of the TLRs. So here you have some examples of computing the sum and the average on a vector of integers. So as you can see, the vector is being passed explicitly as an argument. Similar functionality can be expressed using the TLRs also from the earlier slide, as you can see here. However, if you have access to the vector or any container of values and you wanted to perform aggregation on them, you would probably prefer to use these aggregate relations instead of the TLRs for efficiency reasons. And also these relations support test mode and generate mode support. So you could either generate a sum or test by either initializing the second argument or leaving it uninitialized. And finally, we've come to this last section. In this section, I'll be demonstrating some examples to give you a better feel for using these facilities in practice. Here's an example to demonstrate some simple grouping. Assuming we have this vector of strings called nums, which is initialized with these strings shown in comments. And let's say we are interested in grouping these strings by their first character, as you can see here in the console output, where the first group is the strings beginning with F, and the next group is the strings beginning with O, and so forth. N is our iteration variable to iterate over the vector. In order to express this grouping, we need two things. First, we need to describe the nature of the group. Here we are saying that the group has key type character and values are of type string. Then we also need to describe the selector function, which given the string, it returns the first character in the string. Now we are ready to express the relational expression. So here we are saying that N is grouped by the first character into G. So G is our grouping logic reference. And now we can start evaluating the relation and iterating over the groups. Here the while loop is triggering the evaluation on R, which is the grouping relation. First we print the key of the group. Now each time the relation succeeds, we get one group. So we print the key of the current group, and then in this block here, we are simply iterating over all the values in the group using the item relation and printing the values out. You can actually simplify this block of code using the write all function, which simply iterates over all values in the group and prints them to standard out. And it also puts a separator as necessary, with the default separator being comma followed by a space, as you can see here in the console output. You can also perform nested grouping. In this example, I'm going to demonstrate a two-level grouping on the same vector of strings from the previous slide. First level of grouping which is the outer group, is going to be by the first character, just in the previous example. Our second level grouping, which is the inner group, is going to be by length of string. So you can see here in the console output, the first group F is subdivided into two groups. The first group with the strings of length 4 and the second subgroup with strings of length 5. O and S have only one subgroup. T has again two subgroups. Notice how we are describing the grouping type. We are simply nesting the inner group as a value of the outer group. So the outer group has key type character and values of type another group. This inner group's key type is size t and values are string. Since we're doing a two-level grouping, we require two selectors, one which gives you the first character and the second which gives you a string, the string's length. By the way, this grouping can be arbitrarily be nested. So for three levels of grouping, you would have group of character, followed by group of size t, followed by group of some other key type, and finally of value string. Now we are ready to express the relational expression. So here we are saying group n by the first character into G1 and then group them by string length. So for 3 levels of grouping, you would have an additional dot then. And for 4 levels, there would be yet another dot then with another selector. Finally, we are ready to iterate over the outer and inner groups. So triggering the evaluation on outer, which will give you one outer group at a time, in G1, we print the key of G1. Then we iterate over each subgroup in G1 using the iteration variable G2 and the relation item. So here we are saying G2 is an item in G1, and then we simply enumerate all the subgroups, print the subgroup's key, and then write all the values in the subgroup, and that gives you this console output shown on the box below. Group by also gives you full control over the order in which the groups are generated. By default, the groups are generated in ascending order of their keys. As you can see here in the console output, the outermost level keys are in ascending order. Same way at the subgroup level, again, the groups are in ascending order of their keys. The actual items being grouped, however, are not in any particular order by default. To see this more clearly, let's take a look at our original single level grouping example. Notice here the elements, the strings in the F group are in no particular order. Coming back to our example. So let's say, for instance, you are interested in generating the outermost level groups in descending order instead of the default ascending order. In this case, you would simply specify an additional argument, which is std greater, which switches the order from ascending to descending. So notice T is now first, followed by S, then O and F. So by default, the sorting is done using std less. You could use std greater to change it to a descending order, or you could provide a custom a function object which could do, for instance, case insensitive comparison in ascending or descending order. Similarly, you can also customize the subgroup ordering. Notice right now the order of the subgroups has not changed. They are still in ascending order. So only the top level grouping is in descending order, but the subgroups are still in ascending order. So you could specify the criteria even at the subgroup level. So instead, let's say here we're interested in switching to descending order also. So you would pass std greater instead of the default std less. Now, as you can notice, the output has changed such that even the subgroups are in descending order. Now, naturally, the question arises, how would you sort the actual items, because they do not appear in any order within the subgroup? For that, you would use the item order member function at the very end of all the dot thens that appear, if there are any. So basically, item order with either less or std greater would either give you a ascending or descending order. In this case, I've used std less, which gives me an ascending order. So you can see that the last subgroup here has actually changed the order of elements from 4 and 5 to 5 followed by 4. Now, grouping in general is quite a useful facility. You could think of several use cases for grouping. For instance, a simple application could be a file explorer kind of program which likes to group the files by the extension or type of the file. A more sophisticated example could be a media library which likes to group, say, the files or the songs first by the artist, then by the album, and finally order the songs within the album by the track number. Now, our next set of examples are going to be in the space of what you can refer to as query expressions, basically issuing SQL-style queries over your data structures. So let's take the simple example. You would like to say find the fourth largest country in Asia by its GDP. So let's assume you have a type called country, which stores the name of the country, the continent to which it belongs, the GDP, and its population. Since we're going to be using this type in unification, this type has two basic requirements. It needs to support equality and assignment. The default compiler-generated assignment operator in this case is sufficient for our purposes, but we do need an explicit equality operator. So assuming the data for all the countries is loaded in this vector countries, then we are ready to express our expression. So here's the query expression. We're basically enumerating all the countries using the iteration variable C, and then we are performing filtering on the data member continent to select only the countries which belong to Asia. And then we are feeding that expression to the order underscore mem TLR, which is going to sort all the Asian countries by their data member GDP. And you specify std greater as the sorting criteria because you want descending order and not an ascending order, which is the default. And then once you have the ordered countries in Asia, you skip the first three because you are interested in the fourth. Now the overall structure of this expression is basically we are chaining the take left operator. So basically we have two take left operators here. And since the take left operator is right associative, we need to put these extra brackets so that foo's value is fed to bar, and then this whole expression is then fed into baz. So those are the two brackets that we've put in place to make sure we get the right semantics. And now we simply trigger the evaluation on the relation and print the first value that's returned by the that's generated by the relation. In this next example, I shall demonstrate the use of aggregation in query expressions. This time our query is to find the country with the largest GDP in each continent. So here we have our new query expression which uses grouping to group the countries by their continent. So the group type is described here. The key type is a string, which is where you're going to store the continent. That's the key type. And the group's value type is country. So this part of the query expression will group C by continent into G. And here's our selector by continent, which returns the continent given a country. And then finally we find the max value of G, which is M, using a custom comparator which compares two countries by their GDP. So G is like a container here. So we're using the aggregation relation max of to find the largest value in the container G. And the largest value here is M, which is also a type country, just like C. And the comparison function is provided here. And finally, we go ahead and print the name of the continent, which is the key of the group, and the name of the country, which is the name member of M, and similarly the GDP of the country. This is yet another way to define the same query. So you will often see yourself looking at multiple ways to express the same query. Here the query is still the same, but we are now using the ability of group by to internally order the values in the group instead of the aggregation relation max. So we're grouping the country by continent into G and then ordering the countries within the group using a custom comparator, which will compare two countries based on their GDP using the greater than operator. So what we're doing here is making sure that the group has the countries in descending order of their GDP instead of the ascending order which we would get if we use the less than operator. So once we have that, we simply trigger the evaluation of the relation, which gives us one group at a time every time it succeeds. So then we print the key of the group, which is the name of the continent, and then we print the name of the first country in that group and the GDP of the first country in that group. So begin is basically a method which gives you the iterator to the first element in the group. G is actually just a container adapter. So we have the begin and end methods which give you iterators to the elements in the groups. In our next example, we will be computing the total GDP of each continent. This example is a little more interesting, so let's build it up part by part. So the first part of this expression simply groups the countries by their continent so that we can now go ahead and total up the GDPs within each continent and then print those totals out. So once we've grouped the countries by the continent, we now go ahead and enumerate the countries in G using another iteration variable C2, which is of type country. And then we select the GDP, or we basically extract the GDP for each country in the group and total up the GDPs using the TLR sum. This expression here in the yellow box, if you're thinking in general terms, is actually performing a transformation from type country to type unsigned long, which is basically saying transforming C2 into GDP. And now we can go ahead and print the solutions. Each time R succeeds, we get one group that gives you the continent's name if you use a key member of the group, and then we print also the total GDP for that continent. Transforming objects from one type to another is generally useful even outside the context of query expressions. And here are a few examples of transformations just to get a feel for them. In this first example, I'm transforming a string to a length of the string using the EQ_MF relation in order to invoke the length member function on the string class. Now here in this next example, I'm transforming the country into a pair of strings. The first element in the pair represents the name of the country, and the second element in the pair is the continent. So first I extract the name, and then I extract the continent here. Now, this is just a different way to do the extraction using EQ_F instead of EQ_mem. So you could very well write this second extraction of a continent using EQ_mem. But just for demonstration, I'm using name dial get. And then once you have both the name and the continent, you use the name dial create to instantiate a pair of strings and pass the name and the continent as arguments to the pair constructor. You could actually clean up this example using lambdas and C++ OX if you have access to that feature in your current compiler. So as you can see here, the second argument to EQ_F is a lambda, which not only creates the pair but also extracts the name and the continent from the other country. There are examples of other transformations here. You could use more complicated IL expressions. In this case, I'm concatenating the name of the continent followed by a colon followed by the name of the country into a string, and then unifying it with C_n. And of course, you could use just regular named functions. So in this case, I'm transforming a country into some sort of encrypted string representation of the country by using an EQ_F. And that brings us to the conclusion of this video presentation. You may download the library from the mpprogramming.com website. A couple of resources for more information would be: one is the user's mailing list on SourceForge. for which there's also a link on the mpprogramming.com website. There's also 3 pieces of useful documentation that's part of the download. One is the reference manual, second is the tutorial, and third is the design of the core parts of Castor. So that's it for now, and thank you very much for watching. Goodbye.